Okay, so this is for chapter 3. In chapter 3, we study matter and energy. First, the defining the matter. Matter is defined as anything that occupies space and has mass. Some type of matter, such as steel, water, wood, and plastic, are easily visible to our eye. Other type of matter, such as air or microscopic dust, are impossible to see without magnification. Matter is composed of atoms and molecules. Matter may appear smooth and continuous, but actually it is not. Matter is ultimately composed of atoms, submicroscopic particles that are the fundamental building blocks of matter. In many cases, these atoms are bonded together to form molecules. Two or more atoms joined to one another in specific geometric arrangement are molecules. Recent advances in microscopy have allowed us to image the atoms and molecules that compose matter. So there are three states of matter. We see starting from the top matter, and then we see these three states. Solid, example of solid matter is H2O, which is the ice, and then the liquid is another state. So example H2O, liquid is water, and then we have the H2O can appears as gas, and this fumes from this water heater is water vapor. State of matter type of solid. A. In a crystalline solid, atoms or molecules occupy specific positions to create a well-ordered three-dimensional structure. So we see this is a crystalline solid. It's well-ordered three-dimensional structure. So we see this pattern, see atom, 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 and in this way, horizontal or vertical or other directions. B, or the second type, in an amorphous solid, atoms do not have any long-range order. So this is one picture of amorphous solid, no long-range order. If you're looking horizontal from left to right, you don't see a long-range order like this crystalline. State of matter, crystalline solid. Sodium chloride is an example of a crystalline solid. The well-ordered cubic shape of salt crystal is due to the well-ordered cubic arrangement of its atom-activity ions. And those ion, positive ion are the purple, negative ion are the green. In sodium chloride, the purple positive ion is Na1 plus. Positive ion Na1 plus, also called the cations. And the negative ion are the chloride and also called the anions. State of matter liquid. In a liquid matter, atoms or molecules are close to each other but are free to move relative to one another. Liquid have a fixed volume, but their atom or molecule are in close contact. Liquid assuming the shape of their container because the atoms or molecules are free to move relative to one another. Water, gasoline, alcohol, and mercury are all examples of liquid matter. State of matter gas. In gaseous matter, atoms or molecules are separated by larger distances and are free to move relative to one another. Since there are empty spaces between atoms and molecules that composes gases, gases are compressible. Gases always assuming the shape and volume of their containers. Oxygen gas, helium gas, and carbon dioxide gas are examples of gases. So this property of a solid and liquid gas is summarized in this table 3.1. And we have this a few columns. The first is the state. We have solid, liquid, and gas. And then we see the atomic molecular motions and atomic molecular spacing, shape, volume, compressibility. So we see the first, the property of the first column is the atomic molecular motion. And in solid, we can see the motion for the molecular or the atomic motion is oscillation, vibration about a fixed point. For liquid, it's free to move relative to another. For those atom or molecule in gas, it's free to move relative to another also. And then the second column or the third column is atomic molecular spacing. In solid, the spacing for the atom and molecule are close together. And the spacing for the liquid is also close together. The spacing for the gas is far apart. This column is shape. So the shape for a solid is defined, and the shape for a liquid is undefined, and the shape for a gas is undefined. The volume, so the volume for the solid is indefinite. The volume for the liquid is indefinite, and I'm sorry. The volume for the solid is definite. The volume for the liquid is definite. The volume for the gas is indefinite. And then the compressibility is for the solid is incompressible, for the liquid incompressible, for the gas is compressible. So classifying matter according to its composition, a pure substance is composed of only one type of atom or molecules. A mixture is composed of two or more different types of atoms or molecules combined in variable proportions. Classifying matter, composition of elements. Element, a pure substance that cannot be broken down into simple substances. No chemical transformation can decompose the element into simpler substances. All known elements are listed in the periodic table. Periodic table can be found on the inside front cover of this textbook, and the elements are listed in alphabetical order on the inside back cover of this book. So the periodic table in the front cover of the book is listed by the atomic number. The one in the back is listed alphabetically by the name of the element. Classifying matter, composition of the element helium, for example. Helium is one example of the pure substance composed of only one type of atom, helium atom. And so we see this helium gas in this inside the balloon. We will see those helium atoms. Classifying matter, composition of compound. A compound, a pure substance composed of two or more elements in fixed definite proportions. Compounds are more common than pure elements. Most elements are chemically reactive and combine with other elements to form compounds. Water, table salt, and sugar are examples of compounds. Compound can be decomposed into simpler substances by chemical reactions. Classifying matter, composition of compound water. And this picture is the water. So in the water, we have the water molecules is H2O, so 2H1O. Water is a pure substance composed of only water molecules. Two elements are fixed in definite proportions, has a unique chemical formula, H2O. Classifying matter, compounds and mixtures. When matter contains two types of atoms, it may be a compound, a pure substance, or a mixture. A compound is a pure substance composed of different atoms that are chemically united, bonded in a fixed definite proportions. A mixture is composed of different substances, maybe elements and a compound that are not chemically united but simply mixed together. Classifying matter mixtures. Air and seawater are examples of mixtures. Air contains primarily nitrogen and oxygen. When you see nitrogen gas and oxygen gas, which means N2 and O2 gas. Seawater contains primarily salt and water. So you see here the example on the top in the gas is air. We see this oxygen where actually is O2. So oxygen, and the nitrogen is N2. So the formula for oxygen, uh, so this oxygen is O2. O is for oxygen, nitrogen N2. Water is H2O. So those are the formula, chemical formula for those substances. Substances can be element or compound. And the table of salt will be the NaCl. Classification of matter. Matter can be either a pure substance or mixture. A pure substance may be either an element such as copper or a compound such as sugar. A mixture may be either a homogeneous mixture such as a sweetened tea or heterogeneous mixture such as hydrocarbon and water. So we see this diagram is how we classify matters. When you see matter, any matter you see, so they can either be pure substances or mixtures. Any substance you can see, air, tree, concrete, sidewalk, and then pure substances can be classified into two types of pure substances, one is the elements, the other one is the compounds. And mixture can be classified into also two groups of mixtures or two different types of mixtures. One is the homogeneous, the other one is the heterogeneous. Examples of elements, so we see here the copper. An element of compound, we see here the sugar. Homogeneous mixture example is a cup of tea. So in tea, we have those water molecule. If you add in sugar, you have the sugar molecule. Then you have those caffeine for the tea, from the tea. Heterogeneous mixtures, we see this two layers of matter in this cup, and the matter on the top is oil. The matter at the bottom is water. So therefore, it's heterogeneous. They are not uniform. The top and the bottom are different. And this homogeneous mixture, top and bottom are the same. You cannot tell the difference with your naked eye. Example 3.1, classifying matter, classifying each type of matter as a pure substance or a mixture. If it is a pure substance, classify it as an element or compound. If it is a mixture, classify it as a homogeneous mixture or heterogeneous mixture. So first is the lead weight. So tell you a lead. So we'll begin by examining the alphabetic list of the pure element inside the back cover of this text book. If the substance appears in that table, then it's a pure substance. That means an element. So lead is in the pure table, so therefore it's a pure element. Sea water. So as we saw before, it contains several substances, including salt and water. It is a mixture. It is uniform compositions. Uniform, that means with our naked eye, we cannot tell the difference. So that's it about this uniform composition. So if you use naked eyes, it appears no difference, no matter where you're looking at the matter. So therefore, we call those type of mixture is homogeneous. Distilled water is not listed in the table of the element, but it's a pure substance water. Therefore, it's a compound. Water is a compound. It has a fixed composition of the composing element, H2O. Italian salad dressing contains several substances and is therefore a mixture. It is usually separated into at least two distinct regions with different composition, and therefore is a homogeneous mixture. At least two distinct regions, solid and liquid. Different kind of matter have different properties. A physical property is one that a substance displays without changing its composition. A chemical property is one that a substance displays only through changing its compositions or changing its identity. The characteristic order of gasoline is a physical property. Gasoline does not change its composition when it exhibits its odor. The flammability of gasoline is a chemical property. Gasoline does not change its composition, the gasoline does not change the composition if not burned, but gasoline changes composition when it burns. Physical and chemical properties. Classify each property as physical or chemical. The tendency of carbon to turn green when exposed to air. So this is the chemical property. Carbon turns green because it reacts with gas in the air to form compound and is a chemical property. B, the tendency of automobile paint to die over time is also a chemical property. Automobile paint die over time because it can fade, decompose due to sunlight, or it can react with oxygen in the air. In either case, this is a chemical reaction. The tendency of gasoline to evaporate quickly when spilled. So this is about vaporization or the change of state from liquid to gas. Gasoline evaporates quickly because it has a low boiling point. So this is a physical property. Then D, the low mass for a given volume of aluminum relative to other metal, which is about density. So that is also a physical property. Aluminum's low mass for given volume relative to other metal is due to its low density. And when the density is a physical property, because if you want to observing or measuring the density, you are not changing the identity of the matter. Physical change and chemical changes. In the physical change, matter changes its appearance but not its composition. For example, when ice melts, it looks different, but its composition is the same. Solid ice and liquid water are both composed of water molecules. Melting is a physical change. In chemical change, matter does change its composition. For example, copper turns green upon continuous exposure to air because it reacts with gas in air to form a new compound, and this is a chemical change. So the difference between physical and chemical changes. The difference between chemical and physical changes is seen at the molecular and atomic level. In physical change, the atoms that compose the matter do not change their fundamental association, even though the matter may change its appearance, does not change chemical bonds. In chemical change, atoms do change their fundamental association, resulting in matter with a new identity, does change chemical bonds. A physical change resulting in a different form of the same substance. A chemical change resulting in complete new substance. Example 3.3, physical and chemical changes. So you want to classify each change as physical or chemical change. Okay, so we need to classify each change as a physical or chemical change. First, the rusting of iron, which will be a chemical change. Iron rusts because it reacts with oxygen in air to form iron 3 oxide, so therefore it is a chemical change. And B, it is the evaporation of fingernail polish remover, which is mainly acetone from the skin. That will be a physical change because it's simply the state change. When fingernail polish remove or evaporate, it changes from liquid to gas, but it remains as acetone. Therefore, it is a physical change. C, the burning of coal. Coal burns because it reacts with oxygen in the air to form carbon dioxide. So this is the chemical change. D, the feeding of a carpet upon repeatedly exposed to sunlight. So there will be a chemical change. A carpet feeded on repeatedly exposed to sunlight because the molecules that give the carpet its color are decomposed by sunlight. So therefore, it is a chemical change. All matter changes in chemical reactions. Matter undergo a chemical change when it undergoes a chemical reaction. In a chemical reaction, the substances present before the chemical change are called the reactants. The substances present after the change are called products. Reactants, products, left, right, usually this way, but sometimes we can do the reverse, and then arrow means the chemical change. The law of conservation of mass. Matter is neither created nor destroyed in a chemical reaction. In a nuclear reaction, significant changes in mass can occur. In a chemical reaction, in chemical reactions, however, the changes in mass are so minimal that they can be ignored. During physical and chemical changes, the total amount of matter remains constant. Law of conservation of mass. Suppose that we burn 58 grams of butane in a lighter. It will react with 208 grams of oxygen to form 176 grams of carbon dioxide, 90 grams of water. So the conservation of mass. Solution. Check the mass of all the reactants. If that equals the mass of all the products. So in this reaction, our reactant is the butane and oxygen. The product is the carbon dioxide and water. And we are given the mass for the butane, for the oxygen, adding this mass of butane, 58, with the mass of oxygen, 28, we get 266 grams. And we are also given the mass of the two products, carbon dioxide and water. We have 176 grams of carbon dioxide and 90 grams of water. Adding these two numbers, we also get 266. So therefore, we see the conservation of mass, which means the conservation of the mass of the reactant and the mass of the reactant equals the mass of the product. The behavior of matter is driven by energy. Energy is a major component of our universe. Energy is the capacity to do work. That's the definition of energy. Work is defined as the result of a force reacting on a substance. The behavior of matter is driven by energy. Understanding energy is critical to understanding chemistry. Law of conservation of energy. Like matter, energy is conserved. The law of conservation of energy states that energy is neither created nor destroyed. The total amount of energy is constant. Energy can be changed from one form to another. Energy can be transformed from one object to another. Energy cannot be created out of nothing. It does not vanish into nothing. There are different forms of energy. Energies can be either kinetic or potential. The total energy of a sample of matter is the sum of its kinetic energy, the energy associated with motion, and its potential energy, which is the energy associated with its position or composition. Unit of energy. The SI unit of energy is the joules, named after the English scientist James Joule, who demonstrated that energy could be converted from one type to another as long as the total energy was conserved. A second unit of energy is the calorie, CAL, the amount of energy required to reach the temperature of 1 gram of water by 1 degree Celsius is 1 calorie. A calorie is a larger unit than joule, so therefore 1 calorie equals 4.184 joule. This equation is exact. All the number here, 1 and 4.184, are exact. A related energy unit is the nutritional or capital C calorie, capital CAL, equivalent to 100 liters C calorie. And this table summarizes those a common unit and also a new unit. You don't have to worry about that too much for the kilowatts. Example, conversion of energy unit. A candy bar contains 225 capital calorie of nutrition energy. How many joules does it contain? Relationship used will be 1 calorie or 1,000 small calorie equal to 1 capital calorie. 1 small calorie is 4.184 joules. So therefore, we will have this solution map. We'll start with the capital calorie. From that, we calculate how much smaller calorie. From the smaller calorie, we calculate how much joules. So we'll use these two conversion fractions. We're starting with 255 capital calorie. 1 capital calorie is 1,000 small calorie. 1 small calorie is 4.184 joules. We cancel out the capital calorie. The small calorie, we only get the joules. So that's 9.41 times 10 to the positive 5 joules. We use scientific notation to conveniently represent a large number or small number, in this case, a large number. Exothermic and endothermic reactions. In an exothermic reaction, energy is released. The total energy of the product is less than the total energy of the reactant. Energy diagram is a diagram like this. So we see going up, the energy increases. And for an exothermic reaction, so the reactant starting at a higher place, the product at a lower place. So therefore, going from the reactant to the product, energy is released. B, in an endothermic reaction, energy is absorbed. The total energy of the product is more than the total energy of the reactant. So where those more energy of the product come from? It comes from absorbing from the environment. So we use energy diagram again, going up, energy increases. We're starting with reactants with lower energy. We're ending with some product with high energy. So where the high energy in the product come from? It's absorbed from other place. We call them environment. Example 3.6, exothermic and endothermic process, classifying each change as exothermic or endothermic. Wood burning in a fire. When wood burning in a fire, and if you're standing by, it is emitting heat into the surrounding, you feel the heat. Therefore, this process is exothermic. When ice melt, it absorbs heat from the surroundings. For example, when ice melts in a glass of water, it cools water as the melting ice absorbs heat from the water. If you drink the water with ice, you feel the cool water. Therefore, the process is endothermic. Do not confuse temperature with heat. Heat, which has units of energy, is the transfer or exchange of thermal energy caused by a temperature difference. For example, when a piece of cold ice is dropped into a cup of warm water, heat, thermal energy is transferred from the water to the ice. Temperature, by contrast, is a measure of the thermal energy of matter, does not tell you not the exchange of thermal energy. They tell you which direction it will go by compare the temperature of different objects. Compare the temperature of water boiling and freezing. For example, in Celsius, Fahrenheit, and Kelvin, we have these three different temperature scales. We have the Fahrenheit scale, Celsius scale, and Kelvin scales. And we know the water freezing in Celsius is 0 degrees Celsius, Fahrenheit 32, and then in Kelvin it will be 273.15 Kelvin. Water boils in Celsius is 100 degrees Celsius, and in Fahrenheit is 212 Fahrenheit. In Kelvin, it will be 373.15. We can converting between temperature scales. We can convert between Fahrenheit, Celsius, and Kelvin temperature scales using the following formulas. You can use the 2 formula or 3 formula. It depends on how you manipulating the formulas. We can start with 2 formula. We say this is the conversion between Kelvin and Celsius, and this is the conversion between Celsius and Fahrenheit. The degree simple is used in the Celsius. So Celsius has a degree simple, and Fahrenheit has the degree simple, but not with the Kelvin. So Kelvin simply the K. Converting between Fahrenheit and Celsius temperatures. So you want to converting 55 Fahrenheit to Celsius. You will substitute the given value into the equation and calculate the answer to the correct number of single figures. So we can say this equation you want to use. If you have this Fahrenheit 55, you can simply substitute into this equation and then do a subtraction, do a dividing. Use calculator, you get more digits, but you keep tracking the single different figure and single different digit. Your final answer will be 13. All right. And in this example, is converting 310 Kelvin to Fahrenheit. You probably first need to convert the Kelvin to Celsius using this equation. Even though this equation gives you the Kelvin, but you can still do some manipulation algebraically. You can just get this equation for Celsius. So now you can just substitute this K by 310 and then get this 36.85. Now you are ready to using this equation to get the Fahrenheit. Again, you can just plug this number in and just solving for the Fahrenheit, or before you plug in, solving for the Fahrenheit, and then plug in. So that's what we did here. We starting from this equation, and we multiply both sides of this equation by 1.8. So therefore, we get the, that means we multiply here by 1.8. We multiply here by 1.8. 1.8 times Celsius. And this 1.8 cancel out. So we get this here. And then what we did is we simply just rearrange, or we adding, so let's see, we're adding 32, and then we have 32 add here. So then these two cancel out. So we get, initially we get the Fahrenheit on the right, and then we have 32 plus 1.8 times the Celsius. So then you can write this on the left side, or you can write this on the right side of the matter. And then these two numbers, you can write whoever first doesn't matter. So therefore, our final answer, we put this Fahrenheit on the right side. And then we write this one as our first. And then we write the 32, but it doesn't matter. Okay, so now we are ready to plug in our Celsius. We get from step 1, and then we get the Fahrenheit. So that's what we did. And then we finally keep the right number of sigma fig, we get 98. Temperature change, heat capacity. Heat capacity this is the quantity of heat usually induced required to change the temperature of a given amount of the substance by 1 degree Celsius. Also, probably also can be same as in 1 Kelvin. When the amount of the substance is expressed in grams, the heat capacity is called the specific heat capacity or specific heat, and it has a unit of joule per gram per degree Celsius or per gram per Kelvin. And so therefore we have this kind of two different capacity. Usually depend on the content of the problem. So we will see what capacity we use. This table tell you the some common matter and the specific heat capacities, which is written here, have this unit. Probably clearly you can write like this: joule per gram and per Celsius. So these two units in the denominator, and the joule is the only one on the numerator. We have this lead, gold, and so on. We have those numbers. Notice that water has the highest specific heat capacity on the list. So here water, 4.184, really much higher than everything else. This data table is needed when solving homework problems, and energy, temperature change, and heat capacities. The equation that relates these quantities is heat equals mass times specific heat capacity times temperature change. And then you can see in mathematically, so heat is represented by Q, mass is represented by M, specific heat is represented by C, temperature change is represented by delta T, or together delta T. And the temperature change in Celsius and Kelvin will be the same. So you can either calculate the delta T in Celsius or the delta T in Kelvin. So either way, you will get the same number. And the Greek symbol delta means the change in something. So therefore, delta T means the change in temperature. Relating heat energy to temperature change. As a gallium is a solid at 25.0 degrees Celsius, melt at 29.9 degrees Celsius. If you hold gallium in your hand, it can melt from your body heat. How much heat must 2.5 grams of gallium absorbing from your hand to receive temperature from 25 degrees Celsius to 29.9 degrees Celsius? Also tell you the specific heat capacity of gallium is 0.372 joule per gram per Celsius. So you can just simply thinking of we are given C, M, delta T. We want to calculate Q. Then see, do we have an equation for that? Yes, we do. We have Q equals M times C times delta T. So therefore, we can most of the problem, the unit will be okay. We can just simply plug those numbers in. Probably before you plug them in, you have to calculate the delta T, because usually will tell you the TF, which means final temperature. And also tell you time, also tell you TI. So that will be our initial time. If you know these two, then do the subtraction, get delta T. Okay, your delta T may be positive, may be negative, depend on the TF and TI. So in this example, we get delta T the positive. So therefore, we will see our Q will be also positive. So therefore, it means endothermic process. It absorbs heat from your hand. So once you get those numbers ready, you have 2.5 grams for M, 0.372. So this will be That's type of here, this will be joule per gram per Celsius. You cancel out the gram, cancel out the Celsius, you get joules. All right. So you keep this, finally keep this 2 sig fig, because this has 2 sig fig, this has 3 sig fig, this has 2 sig fig. So therefore you have 2 sig figs. Another example, relating heat capacity to temperature changes. A shining rock was suspected to be gold. The rock has a mass of 14.3 grams. The temperature of the rock rises from 25 degrees Celsius to 50 degrees Celsius upon absorption of 174 joules of heat. Find the heat capacity of the rock and determine whether the value is consistent with the heat capacity of gold, which is listed in this table. So if the matter, the rock is gold, and then it will have this specific heat capacity 0.128. So we see our problem is we are given those informations and we are given the mass and heat and the temperature change. So therefore we can using this equation and solving for the C, which is the specific heat capacity. So we just rearrange this equation. What we did is divide this both sides by m and delta t. And then we divide also here by m and delta t. So m comes out, delta t comes out. On this right side, we won't have c. And then on the left side, we'll have that, whatever that. Then we have equation, left side by right side can change. So therefore we write the C on the left. We have this equation. So then we just plug in those numbers. Again, before you plug those numbers, you probably want to calculate the delta T here. Okay, so our delta T, it will be the T final or TF minus TI. So we know our TF is 52 Celsius and our TI is 25 degrees Celsius. So therefore we have 27 degrees Celsius. And that is our delta T. And that is our delta T. So we plug those numbers in, and obviously we did not cancel out any units, therefore we have joule, we have gram, we have Celsius, and therefore we have this unit, which is the unit for the specific capacities. And we have 0.45. Obviously, that is not the number for gold. So therefore, our conclusion from this simple calculation for the heat capacity, we see the rock is not pure gold. Okay, so this is the learning object of this chapter. As you usually will just go by those learning objectives to review